All right, today we're going to talk about radiation. And if radiation sounds like something you talked about in math, it's because that is exactly where the name comes from. Right? The idea of a ray in math is something that starts at a point and then moves off in a direction until it can't be stopped. And that's actually exactly what radiation is. It's this idea that we're going to generate something that's going to start somewhere and then move until it impacts something else, or move until it hits something else. And that's where the original idea of radiation came from. There are sort of two classes of radiation. There is energy radiation, and then there is particle radiation. And energy radiation is kind of divided into two subclasses, okay? In energy radiation, there's what we call non-ionizing and ionizing radiation. And some people call particle radiation ionizing radiation, but that's true. There is no particle radiation that's not ionizing. So you could totally call three different categories here of energy that is non-ionizing, energy that is ionizing, and particle. What makes radiation non-ionizing versus ionizing is its energy. The non-ionizing radiation is low energy stuff, all right? So non-ionizing radiation, energy radiation is stuff like light. Light, you can sit around all day underneath a lamp, the lamp on your desk or the lights here in school, and it will not ionize the atoms in your body. Other things like, believe it or not, microwave radiation and radio waves, radio radiation. Your cell phone and your Wi-Fi both kind of fit in this microwave and radio radiation end of the spectrum, and we're glad they don't ionize anything, because otherwise using your cell phone would cause cancer. So, kind of glad for that one, right? But ionizing radiation is, for energy radiation, it's stuff that has high energy. And really, all particle radiation has more energy than any of the energy-based radiation. High energy radiation, ionizing radiation, are things like X-rays. There are things called cosmic rays. Cosmic rays, to me, are the really scary ones. Cosmic rays are these super, we like to call them greasy photons, but these super high energy packets of radiation that are bombarding the Earth from space. They're called cosmic rays because they're coming from space, and some of them have a massive amount of energy, and we have no idea where most of them are coming from. In theory, right, one of the theories that's been suggested actually is that there's some alien civilization out there that's decided it hates us, and they're firing packets of radiation at us. They hit the Earth in very, very sparse numbers, and so the idea that a cosmic ray would hit you is very low in probability, and the idea that it would hit one of your cells is even lower, and the idea that it would hit your nucleus even lower, and the idea that it would hit an atom in your DNA super duper low. So there's not a lot of danger from cosmic rays because they're just not that many of them, which is but it's still kind of spooky to think that there's these super dangerous radiation rays that are hitting us. Gamma rays are also very energetic ionizing radiation, and all of these have a wide range of energies that they come from, that they pull from, but they all are dangerous to the body. Now, gamma rays are the ones that we spend the most time talking about in chemistry, so they're going to be the ones that are the most important to us out of this group. Particle radiation, there are basically three types of particle radiation. I'm going to move my screen over here so you guys can see this. There will be a name for each one. There will be a symbol for each one. And there will be a charge for each one. Okay? And we're going to go by order in which they were discovered, and they're named in the order in which they were discovered. So alpha radiation was first. Alpha radiation, as it turns out, is just a helium nucleus. So it is helium, and it has a mass of 4 and an atomic number of 2. So good reminder for you, right, to see these symbols, right? This one right here is the atomic mass, or A, and this one is the atomic number, or Z. And I'm just now realizing, as I'm looking at that, I wrote those backwards. Okay, let's fix that. Let's fix that, shall we, right? So we're going to put a 2 on the bottom, and we're going to put a 4 up top. There's the atomic mass, and there's the atomic number. All right, so now that I've fixed that, super important to get those right? Yeah, atomic mass goes on top, atomic number goes on the bottom. There we go. The charge, because the helium nucleus, it doesn't have any electrons on it to counteract those 2 protons that are in the atomic number. Good review of Penzac for you right there. The charge of alpha radiation is positive. It is actually a positive 2. And when they first discovered it, the reason they discovered it, I'm going to add one more column on here. Let's talk about the size of it. The reason alpha radiation was the first one discovered is because it is huge. It is very, very large. It is the largest radiation. It was the easiest one for them to capture, the easiest one for them to see, because it has a charge, very massive size. The second one discovered was beta radiation, because, by the way, the word alphabet comes from the first 2 letters in the Greek alphabet, alpha and beta. But you learned something today, right? The symbol for beta radiation is just an electron. So because it's just an electron has a mass of 0, and it has an atomic number of -1, which is super duper weird. The charge on it, the charge on an electron, is -1. And its size is, it is teeny tiny. It is a small packet of radiation, just a tiny packet of radiation. And neutron radiation was the next one discovered. It took them a while to find beta, but it took them even longer to find neutron radiation. The reason is, if you look at a neutron, it has an atomic number of 0. It turns out it's a lot easier to find something that's got a charge, because neutron radiation doesn't have a charge. It's very difficult to identify, very difficult to find it. Its size is kind of, we're going to call it medium, because it's in between the other 2. All right. Now, technically, all right, these are the 3 particle radiations. All right. There is one more radiation that we tend to include in this chart, even though it's not a particle. Chemists often treat it like a particle, because just like these other ones can be created, we can also create this other packet of energy, and that packet is gamma. So what we're going to do is we're going to add gamma radiation. Even though it's not a particle, we'll add it to this chart. All right. The symbol for gamma radiation is kind of fun to draw. It's like a fish standing on its head. And so there it is. It's a fish standing on its head. It has 0 charge, and it has 0 mass. So it's 0 charge and no size. There is no mass to gamma ray. It's just energy. So if you want in your brain asterisk that one is a little bit special. Gamma radiation technically is not particle. All right, but it belongs in this chart because we're going to use all of these to show how they interact with atoms, how they interact with isotopes, how we make new isotopes using these. Technically speaking, you can use anything as particle radiation. And right down the road here at Oak Ridge National Lab, there's something called HIFER, the high flux isotope reactor, where they take all sorts of weird atoms and turn them into radiation and bombard things with that weird radiation. And they do that to make man-made elements, to make the elements on the periodic table that don't exist in nature, pretty well everything past uranium. And that's kind of fun, and that's what we're going to talk about in this unit. To do that, we're gonna talk about one last thing with these radiation particles, and that is penetration. If you are going to work with radiation, you do not want it penetration. There we go. There's spelling in there somewhere. Shun. There we go. Penetration. So penetration is really important when you talk about radiation because you want to be able to hide behind something to get away from the radiation. You ever notice when you get like a dental x-ray or any x-ray really on your body, the x-ray tech, the person who's running the device, runs and hides behind a brick wall, right? That's because x-rays, which are very close to gamma radiation in the way that they interact with matter, X-rays will penetrate anything but the most dense concrete, and so they like to go behind. And what's weird is when I go to my dentist's office, the only brick wall, the only cinder block wall they've got in the entire building is in that that X-ray room. But they do that because they don't want to get a massive dose of radiation several times a day, right? It's all right for you to get it once, but they don't want to do it like 20 or 30 times a day. So, and the penetration power of each of these radiations is related to their size. So a large particle needs very large pores to go through. So believe it or not, alpha radiation will not penetrate skin. It won't go through anything that is thicker than skin. So alpha radiation is really only dangerous to you if it gets inside your body, because then it can reach your internal organs. It can reach your atoms, your cells that are inside your body, right? They're inside your DNA, and that's where it becomes dangerous. Beta radiation won't go through basically, it won't go through about a half an inch of wood. So beta radiation, your flesh, for the most part, protects you from beta radiation, right? And so beta radiation can't reach things like your bones because it can't get through your skin and your flesh to reach the deep down bones, right? Bones that are close to the surface, like your fingers or these bones in your hand, you can get hit with beta radiation. Neutron radiation is really difficult to stop. And you say, well, it's medium size. You say it's kind of based on size, but it's also related to the charge. Because neutron radiation doesn't have any charge, it doesn't really interact with matter very well. So you really need, to protect yourself from neutron radiation, you really need something very dense and very heavy. And lead is the biggest thing. And by the way, both neutron radiation and gamma/X-ray radiation kind of behave the same way, right? They won't go through something super duper dense like lead. So that's the types of radiation right there. That's how they break down. Next, we're going to show how these things interact with atoms, how they interact with matter.